Hello my dudes, and welcome back to Viewfinder Engineering. Today, we're going to be learning how to sketch Bode plots by hand. Let's start off with some background. Bode plots show us how a system is going to respond to different input frequencies. If you think back to when we learned how to calculate gain and phase, you'll recall that we solved for both in terms of some generic input frequency omega. But when we plug in different values for that frequency omega, we find that our system output has varying gains and phase shifts. Let's take our random system mv dot plus bv equals f naught sine omega t, for example. Now, we previously found that this is our gain and this is our phase shift, but let's look at how it behaves over a variety of frequencies. At an input frequency of 0 radians per second, which is also a constant input, we find that our gain is 1 over b and our phase shift will be 0 degrees. Playing around with it a bit, we see that by increasing our frequency to 10 radians per second and 100 radians per second, we get very different results for our gain and phase shift. And this is easy to do for a few calculations, but what if we want to calculate our system output over a wide range of frequencies, maybe over all input frequencies? That's where our friend the Bode plot comes in. But before we can get to talking about our system response, we gotta talk about these axes. Bode plots are drawn on a semi-log scale. That means that on the x-axis, each major tick mark is an increase by a factor of 10. So, if our first tick mark is 10 to the 0, that would be 1. Our second tick mark will be 10, our third 100, etc., etc. The y-axes for both gain and phase are usually in a normal linear scale. However, sometimes people like to be tricky and put gain in terms of decibels. Seems suspicious to me, but whatever. Matlab does it this way, so it's just something to be aware of. And in case you're like me, when I started this course and you have literally no idea what a decibel is, it's just another funky logarithmic scale. So now that we've got our scales down, let's label some axes. On the x-axis, we have our input frequency omega, which will be in radians per second. And it's at this point that I want to talk about these funky double x-axes you've probably noticed. Now, these are just to denote that the top half of the graph and the bottom half of the graph are two separate pieces. So as opposed to like positive and negative, this is one chunk and this is a separate chunk. Kind of confusing, but it'll make sense once we get into it. So on the top half of our graph, we have gain, which I'm going to label G. And on the bottom half of our graph, we have the phase shift, which I'm going to denote phi. Yes, that's a phi. It's special, but whatever. And while we're talking axes, we might as well talk units. Gain will usually be unitless or in decibels. And remember, this is just because gain is the ratio of our output to our input, so the units cancel out. And then phase shift down here will be in degrees. So before we continue on, I feel like I should probably make a disclaimer. Personally, I find it much easier to read and interpret Bode plots once you know how to sketch them, but I understand that this isn't really how most courses are set up. So if you're just looking for like basic first and second order systems and interpreting Bode plots, but you don't really want to get into the why of it all, then I'm just going to link my video somewhere around here and in the description below that covers Bode plot basics, and that might be a little bit more helpful to you. But still, this is good stuff to know, and it's super useful in the long run, so I still highly recommend watching the rest of this video. Nothing to do with the fact that I want you to watch the full video, but whatever, you know? So, let's get to making some beautiful, beautiful artwork. Now, step one might seem a little bit obvious, but first we're just going to draw our axes and label them. So, if you remember, our horizontal axis is our input frequency, which will be omega in radians per second. The top half will be gain, which is unitless, and the bottom half will be our phase shift, which is in degrees. For step 2, we mark the magnitudes of all of our poles and zeros on the frequency axis. As a refresher, don't forget that the poles are our system's eigenvalues. They're on the bottom half of our system transfer function, and the zeros are on the top half of the transfer function. Now, I know that we want our poles to all be negative so that our system is stable. But that doesn't mean we're going to have negative values on our frequency axis. So the key word in this step is magnitudes. And same thing with our complex eigenvalues. We don't want them to be off on the imaginary plane somewhere. Magnitudes is important. So let's just pretend we have poles and zeros with magnitudes S1, S2, S3, and S4. We're just going to draw them on our horizontal axis. Once we've done that, we move on to step 3, which is sketching our gain asymptotes. Starting at the y-axis, we need to find our DC gain. This is the gain for our constant input, so we do this by plugging 0 into our gain equation for omega. Now, if our DC gain is 0 or infinity, this messes with things a bit and we have to start from a different place. But generally the DC gain will be a real number, so that's what we're going to cover in this video. After we mark our DC gain on our y-axis, we take our asymptote across horizontally until we hit one of these frequencies that we marked in step 2. The slope of our asymptote will increase by 1 for every pole we hit and decrease by 1 for every 0 we hit. Now, it's important to note that in the case of complex zeros or poles, there's basically 2 frequencies smack dab on top of each other. So, for a complex pair of poles, you would decrease by 2 instead of 1. And for a complex pair of zeros, you would increase by 2 instead of 1. And just for clarity's sake, we finish up step 3 by marking the slope of each of our asymptotes. And this may seem kind of mundane, but let's be real, engineers don't always have the best handwriting, and the last thing we want is to get this wrong on a test because it looks like a -1 and our professor thinks it's a -2 or something. Now that was kind of a lot of information, so just to recap our Mongo step 3, we're sketching our gain asymptotes. So poles mean you subtract 1, zeros mean you add 1, and we always start at our DC gain. For step 4, we need to label the actual values for our DC gain and also the values at each of our corner frequencies, which I may not have said before, but corner frequency is what we're going to call those magnitudes that we found in step 2. Our asymptotes gave us a pretty good idea of what our graph is going to look like, but we still need to find numeric values for each of these points. So we already established that we find our DC gain by plugging in omega equals 0 into our gain equation. And that's going to be our jumping off point. From there, we can use the equation g1 over g2 equals omega 1 over omega 2 times the slope to get our first corner frequency. Then we can take that point, use the same equation, and get our second one. And just keep doing that until we have all of our points. So I didn't put any numbers into this example because it's not a real equation, but let's just pretend that each of these dots marks a numeric value that we found. And last but not least, well, at least for the gain, we still have phase, but anyway, step 5, we connect our points together, and this will give us the actual plot of our gain. Now, it's important to note that sketching this by hand just gives us an approximation of what our actual graph is going to look like. For example, if we had resonance at one of these corner frequencies, this doesn't take that into account. However, this is still going to give us a really good idea of how our system behaves. So for step 6, we're now transitioning down to our phase shift. And we start similarly to the way we started with gain. We need to calculate what our phase shift is going to be when omega equals 0. And this angle is what we're going to mark on our y-axis. Much like in step 3, we're now going to work our way across and change our asymptote every time we hit one of our corner frequencies. For every 0 we hit, our phase will shift up by 90 degrees. And for every pole we hit, our phase will shift down by 90 degrees. So the same thing applies for our complex poles and zeros too. A complex zero means we shift a positive 180 degrees, and a complex pole means we shift negative 180 degrees. And last step, for real this time, step 7, we draw in our angles. Now, our phase line will have a bit of a curve in it as it passes through each of our corner frequencies, but the important thing to note here is that at the corner frequency, our phase shift will have completed half of its transition. So like, if it's dropping from 0 to negative 90 degrees, at that corner frequency, the phase shift will be negative 45 degrees. And again, we have the same disclaimer as we did with gain. You know, this is just an approximation. It's a super helpful tool, but this doesn't quite get all of the nuances and stuff. So just something to keep in mind. So the transition might be faster or slower than we draw it out in our approximation, but the important thing is that we have a good idea of how our system behaves. Now, that was a lot of info, but we did it, boys. So to kind of solidify that in our brains, let's walk through an example. So let's look at our system x triple dot plus 101 x double dot plus 101 x dot plus 100x equals f dot plus 10f. And just for simplicity's sake, I'm going to go ahead and say that we know our characteristic equation is s squared plus s plus 1 times s plus 100. And if you're wondering what this is, it's my final exam, because this was a question that was on the final exam in multiple places. So the more you know, Bode plots are important. So before we can even begin to follow our sketching steps, we need to pick out some key information from our system equation. And to do so, we're going to start by taking our system transfer function. And to go ahead and simplify things even further, I'm going to factor out our denominator using this information that we have from our characteristic equation. Now that we've done that, we need to find all of our poles and zeros. It's pretty easy to see that we're going to have a 0 at s equals negative 10 and a pole at s equals negative 100. But we're going to have to use our good old friend, the quadratic formula, to get our poles from this little piece of the equation. So we find that we have a 0 at negative 10 and poles at negative 100 and a complex pair at negative 1/2 plus or minus square root of 3 over 2j, which I forgot the j. There. The final step we need to take before we can start sketching our Bode plot is that we need to find the magnitudes of our zeros and our poles, which we can do pretty easily. So we're going to have corner frequencies at 10 radians per second, 100 radians per second, and 2 at 1 radian per second. Now it's time for some beautiful art. Step 1, draw and label our axes. Now don't forget our x-axis is going to be on a logarithmic scale here. So we're never quite going to reach 0, we're just going to get to smaller and smaller decimals. For this example, I'm going to start our x-axis at 10 to the negative 2, because based on our corner frequencies, we don't really need to go any smaller. Which brings me to step 2, which is marking our magnitudes. This example is super convenient because everything is in a multiple of 10, so all of our corner frequencies are going to look pretty on our logarithmic axis. So, as we found in our transfer function earlier, we're going to have corner frequencies at 1, 10, and 100. Now, on to step 3. Let's draw us some good asymptotes. For starters, we need to make sure that our DC gain isn't 0 or infinity. So, using our equation for gain, we find that at a frequency of 0, our gain will be 0.1. Not 0 or infinity, it checks off. We're going to start by marking it on our y-axis and then extending out our horizontal line. Now, the first corner frequency we hit is 1, which is our pair of complex poles. So, we know the slope is going to drop by negative 2. Next, we hit our corner frequency of 10, which corresponds to our 0. So, we're going to add 1 to our asymptote slope to get a slope of negative 1. Finally, we hit our quarter frequency of 100, which corresponds to a pole. So our asymptote slope will go back down to negative 2. And don't forget the last piece of step 3, we need to label these, because clearly I'm not an artist and my -1 and -2 kind of look similar. For step 4, we can go ahead and start by labeling our DC gain at 0.1, which we found earlier. We then got to use our math skills to find what our value is going to be at each of our corner frequencies. Now, if you remember from earlier, we're using this equation to calculate everything. But this video is already getting kind of long, so just for the sake of time, I'm not going to do all those calculations right now. I'm just going to place these dots up on the board, and we're going to pretend like they're super accurate. So to finish up gain, we have step 5, which is just connecting the dots. Voila! For step 6, we're going to move to our phase shift. Now, we already know from math that our phase shift at 0 is going to be 0 degrees. So I've already marked that on the plot. However, if you're not quite convinced, you can always go back and calculate that yourself. It's just getting a little too much for this video, you know what I mean? So, anyway, now we're going to draw our asymptotes. We first extend our horizontal asymptote out until 1, where we hit our first corner frequency. Since it's a pair of complex poles, we know that we're going to drop by -90 degrees times 2. Because remember, there's really 2 values here at this corner frequency. So this 0 degrees turns into -180 degrees. We stay down here at -180 until we hit our next corner frequency, which is a 0. So this now hops back up to -90 degrees. And that will stay there until it hits our final corner frequency, which is 100 and is a pole. So we drop back down another 90 degrees. And finally, in step 7, we connect the dots again, remembering that we will have undergone half of our transition at the actual value for the corner frequencies. So there we have it, folks. We did it. 10 out of 10 proud of everyone here. Solid work, my dudes. Now, because we're going to go the extra mile and plug this equation into Matlab to double check our work really quickly. Now, I apologize because I know this lesson is already getting kind of long, but we're just going to fly through this really quick to prove that drawing things by hand gives us a really good approximation of what they actually look like. So, luckily we exist in 2020 and computers are a thing. So we can easily check our work using just a few lines of code. For starters, I'm going to clear everything up here and we can get into it. Using our handy dandy transfer function tool, we can quickly set up this system. Then all we gotta do is use our good friend Bode and magic, a beautiful Bode plot. Now we can see that it's in decibels, which are kind of gross, but the important thing is that our shapes match. We could go in and manipulate our data to get our gain axis on a linear scale, but that's not really the point of this video, so I'll save that for another time. Maybe in a video that hasn't been so obnoxiously long. But if you're still here, thanks for sticking with it. You've made it through. Have a gold star. You deserve it. Thank you so much for watching. Be sure to give this video a big thumbs up if it helped, and to smash that subscribe button if you want to see more content about college level math, and engineering, and science, and all that jazz. Okay, bye!